So I've got this. This is a canal here. This is water. This is a boat. I know it's a terrible drawing. It's a boat in water, and I got two guys with ropes that are trying to pull the boat down the canal. This guy over here is pulling. This is a 20-degree angle from straight down. This guy's pulling at a different angle, a 25-degree angle. And here are their forces. Force is measured in units called newtons. So this guy's pulling with a force of 5 newtons. He's pulling with a force of 7. We want to find the net force in both magnitude and direction. Okay, so let's draw these out as vectors. So F1, this guy's force here. Magnitude is the hypotenuse, and it is always positive. This is a 20-degree angle right here. And the magnitude of that force is 5. Remember, magnitude is the hypotenuse, and it's always positive. I'm going to draw in this triangle here. So this side is 5. If that's a 20-degree angle, this is a 70-degree angle. Over here will be the y component of that force, and this will be the x component of that force. In order to add vectors, we have to write them in component form. You can't just add, oh, 5 plus 7. Our net force is not going to be 12. These guys are kind of pulling against each other a little bit. To add vectors, you have to write them in component form, then add the x's and add the y's. So I need to write both of these vectors in component form. So let's look at this right triangle here. Magnitude is the hypotenuse of the triangle, and that's always positive. Across from the 70-degree angle is F1y. So F1y, the y component, will be magnitude of F1 times the sine of 70 degrees, because it's opposite the 70. F1x will be magnitude times cosine. Okay, now we have to put in the pluses and minuses ourselves. So I'm just using this reference triangle here, and I wanted to use that 70-degree angle because that lives against the x-axis. I could have used the 20. I could have done this. That would have been perfectly fine. And I could have said across from the 20 is the x. So F1x would be magnitude of F1 times sine of 20. Sine of 20, cosine of 70, those are the same. So either way, we could draw either triangle. Now, but I need to put in the pluses and minuses myself. Look at this y value. That's a positive y, but look at this x, that's a negative x. So I have to put in that negative myself. So this will be 5 times the sine of 70 degrees and 5 cosine of 70 degrees. So let's type those in our calculator. Make sure you're in degree mode anytime we're doing vectors. So 5 sine 70, 4.70, and 5 cosine of 70, 1.71. Okay, now we got to put in the negative ourselves. So this x value here is a negative. So F1 written in component form as a vector is negative 1.71 comma 4.70. It's got a negative x and a positive y. We played the same game for F2. So his magnitude is the hypotenuse, 7. This, we were told, was a 25-degree angle. So in this triangle that I'm drawing, this would be a 65-degree angle. Here's my y component. the vertical component and my x component. Notice they're both positive. They both point in quadrant 1 here. So again, if you're not sure how I'm doing this, just write out sine. If you're not sure what to do, write down sine. Sine of 65 degrees would be opposite over hypotenuse. Hypotenuse is the magnitude, and that's always positive. Now solve that for f2y, just by multiplying that guy over. So f2y is the magnitude of the vector times the sine of 65 degrees. Similarly, the x component in this particular case will be magnitude times cosine of 65. So that's what, 7? Is that what our magnitude was? Sine 65 and 7 cosine of 65. Notice those are both positive. So we get our calculator out. 7 sine 65, 7 cos 65. So we get, what do we get? 6.34 and 2.96. So F2 as a vector in component form is the x comma the y. We've got to be careful here. Get these in the right order. 2.96 comma 6.34. Remember, when we're writing vectors, we're not writing a point, so we use these angle brackets, not parentheses. Parentheses mean points. All right, now that we've got both vectors written in component form, that's always our first step. Our net force, F net, also called the resultant force, we just add these two as vectors. So we just add them up. Add the x's, negative 1.71 plus 2.96, comma, add the y's. Okay, so what do we get there? I won't bring up the screen, but that was negative 171 plus 2.96, 1.25 is my x component. And then for the y, we had 470 plus 6 something, 634, 11.04. That's a bracket. So that's my net force. Let's draw that vector out. That vector would look something like this. Here's my F net. So these guys are kind of fighting each other. Look at their x components. This guy's pulling to the left and up. This guy's pulling to the right and up. Their x's are fighting each other. His is negative, his is positive. Their y's are combining together because they're both pulling down the canal. So our net force is this guy over here is winning a little bit. He's going to end up pulling this barge over to the right. It's not going to go straight down the canal. He's winning because he's pulling at a steeper angle and he's pulling harder. There's 2 reasons he's winning. So the barge is going to end up going toward him. We want to figure out that net magnitude of force. So this is measured in newtons, but that's still in vector component form. We want to find the magnitude and the direction. We want to figure out at what angle it's going to be going down the canal. Okay, so here's my net vector. So if I were to, let me redraw that a little prettier. This is 1.25. This is 11.04. Magnitude is the hypotenuse, the magnitude of a vector. is just Pythagorean. 1.25 squared plus 11.04 squared. Pull that up on the screen so you can watch me type that. So I want square root. Oh, get out of there. Square root 1.25 squared, got a button for that, plus 11.04 squared, hit enter, 11.11. Remember, the magnitude of a vector will always be longer or bigger than either side. So my net force is 11 newtons, 11.11 newtons in magnitude. Now we're going to find the direction. So let's find, let's say this angle right here. Let's call that angle theta. So I could say this is true, tangent of theta, just look at my triangle there, is opposite over adjacent. You've taken trig now. The entire purpose of this class was to learn how to solve this problem. This is what we've been doing all semester. You know trig, trust your trig. To find an angle in a triangle, just use trig. Use sine if you want. You know the hypotenuse. Use cosine, use tangent. So let's undo that. This angle here will be the inverse tangent of 1104 over 125. Make sure you're in degree mode. So second tangent, 11.04 divided by 1.25. That's an 83 point, let's just call it 5-degree angle. Now we got to be careful here. Anytime somebody asks you for direction, you have to say from something. Direction is never just a number. It's not an angle. It's an angle from something. So what do we mean by 83 degrees? I can't say from the x-axis. Look at my original picture. There's no x-axis there. I made up the x-axis when I drew this coordinate system. I have to give the angle in relation to something that makes sense in the picture. So what we're saying is the net force is here. This was an 83.5 degree angle. Let's find this angle then from straight down the canal. And then we can say, I mean, we can see what it is. It's what, 6.5 degrees. In here is a 6.5 degree angle. The net force will be 6.5 degrees from straight down the canal. Notice I used the word from. 6.5 degrees from straight down toward F2. So here's my magnitude. That's something I would ask for. And then the direction, I need some space here. When I ask for direction, you have to use words. I would say 6.5 degrees from straight down the canal toward guy number 2.